Okay, today class we will discuss regarding antenna measurements. Okay, so up to now I have discussed so many parameters. So like the antenna, directivity, gain, and we have seen different types of antennas. Okay, so here antenna means, for example, if I want to test an antenna, for example, this is my antenna. If I want to test this antenna, what is the setup I want to do? Okay, for example, this is my given antenna here. So if I want to measure or if I want to take this any characteristics of this antenna, okay, what is the setup I want to maintain and what is the setup I should fix such that to measure all the characteristics of this antenna. Okay, so let us see here what is the setup for measuring various parameters of an antenna. Okay, so let us discuss the first one, measurement of antenna pattern. Okay, antenna pattern or radiation pattern. So measurement of radiation pattern. So if you take, if you draw the radiation pattern, from that radiation pattern, we can generate different number of uh, from the radiation pattern, we can calculate various number of parameters. Okay, so this is the very important setup for measuring radiation pattern. Okay, so see here, for example, any antenna if you want to test, for example, this is my transmitting antenna. Here I have kept my antenna. So this is my antenna. This antenna is called as an AUT. AUT means antenna under test. AUT means antenna under test. Okay. So here I have kept my transmitting antenna. Here I have kept my transmitting antenna. This is my transmitting antenna. Okay. So let us consider. So from this, the signals I have, the signals it is transmitted, whatever the signals that are received by receiving end. Okay, so based on this, I will calculate all the parameters. The first step is if you want to test any antenna. Okay, so if you want to test any antenna, the minimum distance you want to keep between the test antenna and the transmitting antenna is the D is equal to 2 lambdas. So the separation distance is equal to 2d square by lambda. The separation distance means any antenna, if I want to test any antenna, so this is my testing antenna. You should not keep your testing antenna very near to the transmitting antenna. You should keep minimum a separation distance. This is the first condition you want to keep, you want to remember while you are setting an antenna measurement setup. Okay, so you should not keep your testing antenna very near to the transmitting antenna. It should be separated by a distance of r is equal to 2d square by lambda. R is equal to 2d square by lambda. What is this d? D is the largest dimensions of this antenna, what you are supposed to test. So the first condition for testing any antenna is the transmitting antenna and antenna under test should be separated minimum a distance of r should be greater than or equal to 2d square by lambda, where D is the largest dimensions of the antenna under test. And second one, whatever the measurement setup you are going to do, the second condition for any setup is whatever the measurement you are going to do, the entire setup. This is, for example, this is my setup. This should be kept in anionic chamber. This should be kept in shielding chamber, that is called as shielding chamber. This is my setup, for example. This should be kept in anionic chamber. This should be kept in anionic chamber or shielding chamber. So shielding chamber, that is called as anionic chamber. Anionic chamber. Okay. To eliminate the effects of external EM, to eliminate the effects of external EMI. For example, if we are testing one antenna here, this is my transmitting antenna, this is my antenna under test. Okay, so if it is not kept in any closed contained anionic chamber, Okay, along this, okay, it may receive some other signals from other antennas also. Okay, not from only the transmitting antenna, it may receive other signals from other different antennas which are surrounding nearby surrounding antennas also. Okay, so in order to eliminate this and perfectly want to test this antenna, compulsorily you want to keep the entire setup in an anionic chamber. Okay, so this the first one things to remember before doing all the experiment is, okay, the separation distance between the first one, the separation distance between transmitting antenna and antenna under test should be, so R is equal to 2D square by lambda. And the second one is the entire setup should be kept in anionic chamber, shielded chamber or anionic chamber, anionic anionic chamber. And the third one, whatever the transmitting antenna you are using, should have high gain. Should have high gain. Okay, should have high gain. Okay, so these are the points you want to remember while keeping any setup. Okay, so these are the three things you want to keep in mind while taking any setup. Okay, now let us discuss the first one. Okay, so how to measure the radiation pattern of an any antenna? How to measure the radiation pattern of an any antenna? Okay, so the setup is like this. Okay, so very important one, measurement setup. Okay, so here transmitting antenna is this. So this is my transmitter. This is my transmitting antenna. So from here, different by using different modulation techniques, a high frequency signal is transmitted and is given to this antenna. The antenna will radiate that signal in this direction. Okay. Now, whatever the antenna you want to test, want to keep here. This is called as AUT. AUT stands for antenna under test. AUT stands for antenna under test. AUT stands for antenna under test. Okay. So here for this antenna under test, it is connected with the rotating unit. Okay. So what is the, this is position indicator, for example. So what it will do is here, so see here, for example, this is my antenna. This is my transmitting antenna. Okay, let us consider TX. It is radiating the signals. Here you have kept your antenna like this. Okay, so for example, let us consider it is theta is equal to 0. Now what you will do is, by using this antenna rotating unit, you will here by using this detector and indicator, here you will notice this at theta is equal to 0 degrees. How much of electrical field, normalized electrical field I have received? Some X. Okay. Now, by using this antenna rotating unit, I will rotate initially, for example, the antenna is like this at theta is equal to 0. So I slowly rotate my antenna like this. Okay, simple, one by one direction. Okay, so for each angle at theta is equal to 0, what is the amount of electrical field received? I will notice in indicator. Means at theta is equal to 0 position, how much of electrical field I have noticed in this indicator X. For example, theta is equal to 10 degrees. I will rotate my antenna by 10 degrees by using this antenna rotating system, and I will note down the value. So at I will rotate my antenna by 10 degrees. Okay, so first initially like this, slowly I will rotate my antenna. Okay, but the transmitting antenna is fixed. The transmitting antenna is fixed. I will slowly rotate my antenna test for various angles, and for various angles, for example, for theta is equal to 10 degrees. What is the normalized field pattern like that? 20, 30, 40. So based on that, I will draw my radiation based on this. So taking these values, okay, based on that, I will draw my radiation pattern. Okay, so let us consider this is equal to theta is equal to 0. This based on these values, I will draw my radiation pattern either in polar plot, or I can draw in linear plot also. I can draw in linear plot also. This is how the radiation pattern, this is how the radiation pattern is measured. This is how the radiation pattern is measured. So this is the very, very important setup. Okay, so once if radiation pattern is obtained, once if radiation pattern is obtained, from this radiation pattern, we can calculate so many parameters. From this radiation pattern, we can calculate different parameters. Once if you obtain the radiation pattern, what are the simple things you can calculate? So once if you obtain the radiation pattern, you can easily calculate what is the what is this one? What you call this? This is nothing but nulls. Okay, so for example, if this is the radiation by taking these values, okay, Z1 like this, by taking these values, okay. So if this is my radiation pattern, okay, so this is my first null, okay, this is my first null, okay, so I can calculate. So beam width between first null. So that is beam width between first null. Okay. And similarly, I can calculate. So for example, this is electrical field. Okay. Half power beam width means when the electrical field has fallen to 1 by root 2 times of its maximum value. 1 by root 2 times of its maximum value means I will draw like this. So let us consider the electrical field. So here this is, let us consider this angle. Okay, where the electrical field has fallen to 1 by root. So this is nothing but half power beam. Okay, half power beam width. Okay, so this is how you can calculate various parameters once if you obtain the radiation pattern. So this setup is very, very important. This setup is very, very important for calculating different various parameters. Okay, so this is transmitting antenna. Okay, transmitting antenna is fixed. Transmitting antenna is fixed. Transmitting antenna is fixed. But whatever the antenna you want to test here, that is AUT, that is rotated by using antenna rotating system and position. For example, theta is equal to 0 here, theta is equal to 10 degrees, theta is equal to 20 degrees. Here you will notice for theta is equal to 0 degrees, what is the normalized electrical field. For theta is equal to 10 degrees, here you will notice what is the normalized electrical field. For theta is equal to 20 degrees, okay, so you will make a simple table like this, okay, simple table like this, theta and n of theta, and from that you can draw the pattern. From that pattern, you can easily calculate the half power beam width and beam width between first. So this is the primary setup for measuring the radiation pattern. What is meant by the radiation pattern? Radiation pattern. What is the definition of a radiation pattern? So radiation pattern is defined as the graphical representation of radiation properties of an antenna as a function of space coordinates. Okay, so radiation pattern is defined as the graphical representation of radiation properties of an antenna as a function of space coordinates. Okay, so this is how you can measure the radiation pattern. Okay, so this is the setup. Okay, so this is the setup. So once I have told that how to measure the half power beam width. Once it is completed, okay, so this angle is nothing but once if the radiation pattern is obtained, okay, so this angle is nothing but half power beam width. And whenever the power has fallen to 3 dB, this is nothing but half power beam width. Okay, so you can calculate half power beam width also. Okay, so how to calculate the direct? Okay, so we have calculated half power beam width. Have calculated half power beam width. Okay, so how to calculate the directivity? So directivity of an antenna is maximum gain. Directivity of an antenna is maximum directive gain. Maximum directive gain. Okay, so it is obtained from the field pattern. It is obtained from the field pattern of antenna from the measured pattern. Okay, so their beam widths both in principal planes means both in theta e direction and theta h directions. Okay, so means if you draw the radiation pattern for both in theta e direction and theta h, for example, theta electrical field component, okay, n of theta in and how much of m, okay, for 0 degrees, 10 degrees, h degrees, and similarly h theta, that is for phi component. Okay, so theta 0 degrees, 10 degrees. So what is the value. If you obtain this, okay, we have the formula. D is equal to, so E plane and H plane. Already we have discussed E plane and H plane. I will look at the E plane and the H plane. Normalized field pattern versus theta. E plane means normalized field pattern n of theta versus theta, keeping phi as constant. H plane means normalized field pattern versus phi, keeping theta as constant. Okay. So once if you obtain the all values, okay, that is maximum gain, the maximum value theta direction and phi direction, we are having the direct formula. D is equal to 41253 degrees by theta E half power beam within theta E direction and half power beam within phi direction. Okay, so this is the formula for the direct. This is the formula for the directivity. Okay, so this is half power beam within E plane, half power beam within E plane, and this is half power beam within H plane, half power beam within H plane. So this is how we can measure the directivity of an antenna. This is how we can measure the directivity of an antenna. So this is the setup. Okay. So similarly, we can calculate the side loop ratio. Okay, so side loop ratio means, so first side loop level. What is meant by the side loop level ratio? It is the ratio of first side loop level to main beam maximum. So this is main beam maximum. This is first side loop level. Okay, so this is my first side loop level. Okay, so how much of this intensity to this one is nothing but this is main loop. So this is the maximum value of main loop. Okay, so this is the maximum value of first side loop. This one or this one. Okay, so this is second side loop. This is third side loop. This is first side loop, second side loop, third side loop. So SLR is the ratio of first side loop to main beam maximum. Okay, main beam max. So simply, so fixing the receiver and rotating transmitting and note on the Emax. Okay, so Emax by E, that is nothing but R. So SLR in dB is equal to 20 log base 10. So this is how you can measure the side